Alright guys, let's talk about limits. So the way I like to talk about limits is by the definition that I created that I feel basically sums it up. If x were some value, then what would y be? And I underlined the word would because sometimes y doesn't exist. Sometimes it's a whole, sometimes there's a vertical asymptote, or maybe it jumps from one value to another. So we're basically predicting maybe what y would be if it was defined, or if it's defined, then what would that defined y value be? So the two things that we're going to go over in this video is direct substitution and approaching the limit of infinity. And we're going to be using concrete x values, meaning that these are going to be rational numbers. We're not going to be exploring any limits to infinity. We're going to be doing that in the next episode. So let's jump straight into it, and so let's try to evaluate this limit. The limit as x approaches 4 of x squared. So it always helps to understand limits by graphing it out. So we know that this is x squared, so it's going to be a parabola. It's going to have a parabolic shape. And so at x equals 4, let's say this is x equals 4. At this point, we know that 4 squared is going to be 16. And so when we think about limits, what we already know about limits, we know that when you approach it from the left side, when you approach it from the right side, is going to be approaching one singular value. And if we follow the function, we can see it approaching this value. We can see it approaching this value. And we know that as it gets 4.0001, as it gets really small, it's going to be approaching this point. So we can directly substitute 4 in here, and we can say that 4 squared is going to equal 16. So the limit of this is going to be equal to 16. And you're like, hey, wait a minute. That's no different from if f of x were x squared, right? And that's no different from f of 4, right? That's the same thing as 4 squared. And you're right, it's just direct substitution. And so this is how limits can be, it's almost just algebra, right? But it's the idea that we're approaching something. And so we're actually going to jump to example 3 because I think it really highlights how sometimes this point can't be defined. And so looking at this, we have the limit as x approaches 4 of x cubed minus 4x squared over x minus 4. And oh, wait a minute, that looks quite complicated. Let's look at what we have. What common factors we have? We have x squared, right? So we know that this is going to be the limit as x approaches 4 because you always want to continue the limit, because if it's going to be equal to each other, then there still has to be a limit. You can't just factor it out, right? So I'm going to put x squared, and I'm going to put x minus 4 over x minus 4. And whoa, the x minus 4s cancel out fortuitously for us, right? And before we cancel it out, we got to think about this original function, because when we cancel it out, we're getting x squared, which is the exact same as this function. But our original function isn't the same, because at x equals 4, there isn't a value. It's undefined. If we were to actually, the first step we should always do is direct substitution. So if we were to directly substitute this, right, we would get 4 cubed minus 4 times 4 squared, which is 4 squared times 4 is going to be 4 cubed. So we know this is equal to 0, and then that's going to be 4 minus 4, which is going to equal 0. So we're going to get 0 over 0. This is called, I'm going to have to go into this graph, I'm sorry, but this is called indeterminate form. And my calculus teacher always told me this basically meant more work. It takes more work to determine the indeterminable, right? More work. So that means you gotta evaluate it further. So first of all, we know that these are going to cancel out, and that this is basically going to be x squared. It's going to show the same parabolic behavior. So we can draw our same parabolic graph, and you can see I left a gap right there. And this is going to be where the point x equals 4 is, because it doesn't exist here. So we define it as this kind of hole looking thing, this kind of 0, O, whatever you want to say. And this basically means that there isn't a point here. If we were to take x, if we were to say this is f of x, if we were to take f of 4, that doesn't equal anything. It wouldn't even, what we would say is it doesn't even exist, right? Because there's trying to evaluate it, even though we can cancel it out, the original function states that this would be 0 over 0, and you can't divide anything by 0. But when we look at it from a limit standpoint, right, from the left side, what changes? Nothing changes. It's the same thing as x squared, but there isn't a point at x equals 4. And from the right side, same thing. So if we approach it from the actual function, we see that this is still going to approach 16. And this is going to be 4 squared, and we can cancel these out, and we can do the same thing with direct substitution. And so when you're using direct substitution, factoring them out and canceling them can be an important tool. And here, even though a limit exists, the actual function doesn't have that point. It doesn't exist. So that's how limits bridge what we know exists and what we know doesn't exist. This is what would x be? Well, it would, if it existed, would equal 16. And so I'm going to try to get into one more example. I'm going to try to be as quick as I can with this. So let's look at this function, limit as x approaches 1 over x minus 1. So now when we think about this, we know that if we plug in, let's try to plug in 1, because direct substitution, always the way to go. So if we were to plug in 1, we would get, I don't know why. So when you're evaluating the limit, you actually don't need to write the limit, right? So I'm going to be evaluating direct substitution wise. So this is going to be 1 over 0, because 1 over 1 minus 1 is going to be 1 over 0. And we can't divide anything by 0. So let's graph it out. Let's see what is approaching infinity, what is approaching negative infinity, what's approaching certain values. So here, this is actually going to display asymptotic behavior. It's going to have a vertical asymptote. If you remember your rules of vertical and horizontal asymptotes. So I'm going to draw an imaginary line. This is going to be x equals 1, but like it doesn't exist on the graph of 1 over x minus 1, but it's helpful to sketch. So when I do that, I'm going to draw it like this, and you're like, how did you get that shape? Well, you can obviously just know that's how the shape is. You can either plug into a calculator, or you can just think about it. When you approach a very large x number, it's going to be approaching 0. When you approach a very negative number, it's still going to be approaching 0, because 1 over a really, really, really large negative number is close to 0, right? But here is the behavior that we really want to look at. So if we look at right here, actually, the way I like to think about it is, if I didn't have a calculator, as this value gets infinitesimally very close to this value, let's say it's 1.00001. It's this very, very small number, right? And we were to plug this in, and we were to plug this into this, and we were to do this over 1. We're going to get a really, 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 you don't write this on your thing, but a really small number over 1. When you divide that, you're going to get a really big number. This is where it diverges into English, but you're going to get a really big number, right? So as you keep on getting closer and closer to this, this is going to keep on approaching infinity. And as you do it from the left side, if we were to look at that, this is going to equal 0.99999, a lot of nines, okay? And this is going to be a really negative, really small number, right? And so that's just going to be a negative, really big number. So that is not mathematics, but that's the way I like to think about it. And usually that helps. And if you're more like, that doesn't make any sense to me, well, you can always graph it into your calculator. So I put it into my Y1, and I just put it into a table, and then you can actually go to the second table set, and you can copy these settings, ask and auto. And so when I do that, you can see that as you approach from the left side, as I was saying, as you keep on getting closer and closer, this value keeps on increasing, keeps on getting more negative, larger negative number, and as you keep on going closer and closer to 1, this is actually this gets farther away. This gets closer as you approach. So actually, if I were to do it like this, you would see it like this. So like as you keep on getting closer, 1.1, 1.01, 1.001, it keeps on getting bigger, right? So I can argue that when I say this value is when I say this, if I keep on going, that's going to be a very large number, 1e to the 11th, right? I think it's 90 billion, 900 billion, I'm not sure. But so let's take this one step at a time. How good are we on time? I think we're going to be okay. I'm going to try to finish this. So to denote that we're looking at it from the right side, we use a positive symbol. And is the way I like to remember is the right side is positive, the left side is negative. So when we use the right side, when we use the positive symbol, we're approaching from the right side. So when we're approaching from this side, I'm going to call this f of x. So this f of x is 1 over x minus 1. And I'm going to say that limit, as it keeps on getting smaller, as it keeps on approaching 1 from the right side, it's going to approach infinity. So take that, try to visualize that and try to imagine it. I know it's hard to even think about, grapple with something that's not even a number. It keeps on growing and growing. But that's going to keep on growing as the smaller and smaller you get to it. It's not going to ever approach a singular number. And so let's look at it from the left side. And so I think it's always important to note that this when it comes before or it comes after it, it's telling you what direction you're looking at, not whether it's negative or positive or anything like that. Because you could have the limit from x minus 1. And you can have it from -1 from the left side. So you can have two negative symbols, and it can get confusing. So always remember, when it's in front of the number or to the right of it, that means it's on direction. And like I said, this negative symbol, let me remove this calculator. I don't know what it's doing over here. But this negative symbol from the left side, we know that the left side is negative, so we know that this is going to be, we're going to approach it from the left side. And so when we approach it from the left side, as we keep on getting closer to 1, we know that this is going to keep on growing to infinity, but it's growing negatively, so it's growing to negative infinity, because infinities can have signs too, apparently, even though it's growing. And when you think about it, it makes sense, because you're growing, but the number that we're looking at is negative. And so, does this have a limit? And the answer is no, it does not, because the limit as x approaches 1, we can say f of x, has to equal the limit as we approach it from the left side. So as we approach f of x from the right side, it has to equal it from when we approach it from the right side. And negative infinity does not equal infinity, right? So there exists no limit here. So we would say we wouldn't say it equals it does not exist, but we would say it does not exist. So I hope that clears some things up clears some things for you. And just to go over to recap what we went over, we basically learned direct substitution. And this is when we basically plug it in. This is no different from when we treat it like a normal algebraic equation. And within that, we have another tool of factoring it out, where we can factor it out and get it to a simpler form, where then we can apply direct substitution, so we can factor, right? And number 2, limits from both sides. I'm going to say infinity, and I'm going to call that parity from both sides. And that basically means that you need to have you need to be approaching the same thing from both sides, right, for a limit to exist. So I hope that helps, and if you have any questions, feel free to put them down in the comments section as below. And if you enjoyed this video, keep on learning math. See you.